Hello and welcome to Build Your Own CPU Part 13. In this episode, we'll be looking at the BIOS and glue logic that hold the motherboard together and provide the services that the CPU needs to run. The source code and all the Gerber files for this will be listed in the links below. I'm afraid this episode is a bit long, it's about 57 minutes, but what I'll do is I'll leave links to each chapter so you can just look at the flow diagrams and block diagrams of each piece of software, and you wouldn't have to look at each individual detailed part of the software unless you was interested, of course. Unfortunately, I can't make this any shorter, there's just quite a bit to go through. So feel free to skip ahead through the chapters. The microcontroller on the motherboard is there to emulate the memory and provide some other I/O functions. Now the code running on it is split into two halves. There's the main sequence and there's the interrupt sequence. The interrupt one does background tasks like generating a random number, reading the clock speed and reading the keyboard. And the values it generates from these tasks are stored in some variables that can be picked off by either the CPU or the microcontroller itself. The number generator, that is saved in the virtual I/O byte number 3. So there's 4 I/O registers that have been emulated here. You could have 256, but we're just doing the first 4. And the clock speed, this is for the actual motherboard. It reads the potentiometer on the board, and that value gets put into this internal variable for the PIC controller to use elsewhere in its main sequence. And the reading the keyboard, that reads the values from the keyboard and does a bit of debouncing on them, etc., and puts the final value into I/O byte 2 for the CPU to read. It's the keyboard input. But it also saves some of the values into an internal variable called PIC keyboard. Looks like it says picky board, but it actually should be PIC keyboard, because the PIC controller uses the function keys to control the clock when you're in manual mode, and the main CPU just uses the other 12 keys on the keyboard. So if we have a quick look at the code for this, here we are, version 1.3 for the new PCB I've designed, because there was a few errors, things needed changing, so that the Gerber file matches this. I had to change a couple of IOs. And we're running on a PIC 24FV 16KA304. That's the microcontroller. You could use a different one, providing you've got the pins there, and it must be 5V tolerant. Now if we just scroll down to the timer software, or the interrupt controller software. That's not it, here we go. Whenever the timer that's configured in the setup, which we'll go through shortly, whenever that triggers an interrupt, it's every 2 milliseconds. Comes in here. Setting up for 2 milliseconds was easier than setting up for 20 milliseconds. So all I did is fitted this counter in here that gets decremented every so often. And if it's 0, then carry on. If not, branch to the end of the interrupt sequence and come back out. We have a 10 in there to start with, so we'll loop around 10 times, which is your 20 milliseconds. Of course, this is dependent on the frequency that you're running the microcontroller at. We're running it at 8 MIPS. If you was to run it at 16 MIPS, then obviously this counter would have to be higher. Next, we do the random number generator. In this, we decrement the value we've got and compare it with 0. If it's not 0, then we just branch down to the next bit down here. If it is 0, then we move a 9 into the random number. So we're counting between 1 and 9. And it just goes through this every time an interrupt happens. So it's just a counter. You'd think that wasn't very random, but when the random number gets looked at in the CPU sequence for doing the noughts and crosses, when it looks there is totally dependent on how quick or slow the player is whenever they hit a key, etc. So this could have counted around 100 times before somebody selects a key. You don't know where you're going to be, so you end up with a nice random number. The noughts and crosses program will eventually at some point need a random square to go to. And that's why it's 1 to 9. That's just the square numbers. So if you've got 3, it picks the third square on the noughts and crosses grid. Once we've done the random number, we then move it into the virtual I/O. So we find the base of the virtual I/O, which is physically stored in RAM on the microcontroller. It then saves it there. So it will be in I/O byte number 3. Then the next thing we do is we want the clock speed. So we call analog input 0, and that will return a value between 0 and 1023. And that value is just put into this internal variable here called clock speed. Just saved there. And that will be used later in the sequence to decide how fast we can actually clock the CPU. It's how fast the T states change, basically. And after that, we call analog input 6, which is read the keyboard. So that will return a value between 0 and 1023. So we've set up where the keyboard buffer is, or keyboard buffer number 1, notice there. And it will also set up picky keyboard. They're the two locations. Well, this isn't quite where the keyboard buffer is. This is just the first buffer. We do a bit of debouncing on this, which we'll get to in a moment. So now we've got the where they are saved put in there. We now look at the actual value that we read in, which will be in W0. When you call the analog, the value always comes back in W0. So we move number 33 into W2, subtract it from W0, and see whether we're negative or not. If we're not negative, then we'll jump onto the next key. So if it is negative, then the value is below 33. If it's below 33, it means nothing on the keyboard has been touched. It should be 0 coming back in, but it could be higher value than that. The actual value that the first key does is about 50, so well, it must be about 60, so halfway between the two. If it's below that, and if it's above it, it will carry down here. Come down to here for the first number. Now the way the keyboard's wired, function key 4 just happens to be the first one on the list, and it will return the lowest voltage, which will give a number somewhere between 33 and 81. So we know we're bigger than 33 because we come through to here. If we're less than 81, then we must have been pressing the F4 key. So that will read that in and put the number 4 into the location pointed to by W3, which back here was where the picky keyboard was. So that's loading the value 4 into the picky keyboard address, and then it branches out, doesn't do any more of this loop because it's found the key already. And then the next one down, if the value coming in was greater than 81 but below 125, then we must have been pressing F3. So we put the number 3 into picky keyboard, and again be between 125 and 171. Then you must have been pressing F2, so we put number 2 in the picky keyboard, and the same again for F1. So that when we are actually, the code is looking at the picky keyboard variable, it will see a 1, 2, 3 or 4, which corresponds to the function keys. Now if it wasn't any of those, we would have come down to this part in the code. So if it's between 216 and 263, we must have been pressing the home key. So we move number 10 into location held in W1, which W1 was looking at the buffer keyboard number 1. We'll be putting a number 10 into that memory location. If it was between 263 and 309, it must have been the 9 key, so we put a number 9 in that location, and so forth with all the keys. You see they're in different orders. That's just down to how the keyboard was wired up. And these values, what I've done is I measured the voltage I was getting from the keyboard, as mentioned in the previous video, and calculated what value it would be, and the value I'll put halfway between these two values here. So number 2, we get a value between 609 and 663. Well, that goes all the way through, and if the value ends up being bigger than 900, there's something gone wrong, you've pressed more than one key, etc. Then it just drops out and says we haven't done anything. It will put the value that we got in W. It takes the keyboard buffer 1, what's in W1, and keyboard buffer 2. Now, at the moment, when you first start up, there'll be 0 in there, and if we press, say, the number 1 key, we'll have a 1 in there. Are they the same? No, they're not. They differ. So if they differ, we branch down to here, and we do a little shuffle here. So we save the value we've got at the moment into buffer 2 and what's in buffer 3 into 3, and then just exit out. Every time we run through this, you'd read the keyboard. So if you're holding the key down for more than 60 milliseconds, you would have run through this 3 times. And if you're reading a good value from the key, you should get the same value every time. So here we check that buffer 1 and 2 read the same. Here we're checking that 2 and 3 read the same. And we're checking it's not a 0. So if that's all okay, we must have a good number. We've read it 3 times and they're all the same. So it's saying good number. So that's our debouncing. We then find the virtual I/O, put it in there, and save the value into where virtual I/O byte number 2 is. So here we are, byte number 2 over here. That's where we save the keyboard number in there. The keyboard number is the actual number on there. Apart from the star and the home key they've got, it's numbers 10 to 11. Branch out, no numbers, just me, branch out. We reset the interrupt counter to 10. So if you was running at 16 MIPS, you'd have to make that a 20 because you'd be coming in every 1 millisecond. And then we pop our W1 and W2 registers, or 1, 2, 0, 1, 2 and 3 back onto the stack and return from that interrupt. So the interrupt sequence is now complete. So now we have a look at the main sequence and the setup beforehand. We've got the CPU ROM code. This is the actual sequence that will be running on the CPU, the noughts and crosses program. Then there'll be variables that the microcontroller will need to use, and where the virtual I/O actually lives, and the virtual RAM. And then we need to initialize some things in the microcontroller before it can do anything. Then we set up the variables. You should always set up your variables to a known state. Otherwise, when you start up, you could have all sorts of things happening. And we'll set up the interrupt, which we just discussed. And we'll clear the graphics screen down. And then we'll find out where the ROM lives. The ROM data is held in with the microcontroller code, but it isn't actually part of the program the microcontroller runs. It's just using its ROM to save our noughts and crosses ROM. So we have to find where it is and remember that. We have a look at the code for that. This is not for commercial use. So if you want to build it yourself, you're free to do so. You may modify it yourself, but please leave a credit to me in there. But you're not to sell this to anyone. If you want to sell it, contact me first. All this source code will be in the link to it at the bottom, so you can get it yourself. So I've been through a little bit of this first of all. This is configuring some bits on the controller, microcontroller. Here's where we're setting our interrupt, enabling those. And here is the actual noughts and crosses program held in the ROM of the microcontroller. So this will be the simulated ROM. So here's the first page of the code. We'll go through all this in another video. And another page. It's all in 256 bytes. So from there all the way down to there is the first bit of memory, first 256 bytes, the first page, ROM page. And then there's a second, third, and there's 8 of those. Now here's the variables that we need to run the BIOS or glue logic. So there's the interrupt counter, which we've already come across, a couple of bytes for that. Here's the clock speed one, so a value gets written into here every interrupt, the reading of the potentiometer, so how fast we're going. And we've got the buffer here for the serial data that we're going to send to the LEDs. So there'll be 27 bytes of that, so I'll just reserve 30 to start with. And this is the pointer that just points to it, so as we're counting through it and sending the bytes out. There's the random number that we start with, but that will get written to the I/O. And there's the picky keyboard value, so that'd be F1 or F4 in there if they get pressed. Then here's the keyboard buffer. So there's the main buffer, but there's the 3 other buffers that all will have to read the same for the debouncing. And here's the virtual I/O, which is defined in RAM. I've defined 12 I/O for that, but we're only going to be using 4 of them. This would be, in the real world, actual hardware registers that you would access, but we are just simulating them. Some flags, then the RAM that needs to be emulated. I've done 512 bytes of RAM, although we'll only be using 16 of them. If you was to write a different piece of software, you'd maybe use more of those. And these are just more definitions for the compiler. So if I use the word pulse somewhere, it means the number 2, and so forth with the others. So you see these T states where T1 says 256. What it's really trying to do is write a number 1 out of the port, but it's a 16-bit port and we're using top byte of it, so all the numbers have to be 256 times bigger. So a T2, so for number 2, we got 512. So yeah, description there. And the LEDs happen to go out of a number 9. I think it might be port C9. This is where you're setting up the serial ports if you're going to use them. Although at the moment it's set for 16 MIPS, that should be 8. But I'm not using them, so I didn't bother debugging that part. This bit of code has to be in every 16-bit microcontroller. It basically just clears all the W registers. That's a microchip thing. That's why it's in capitals. You have to have that or the processor won't run. The microcontroller, that is. And right, we've come into the setup now. First thing you do is set all the inputs as digitals, and then set them all as inputs and some outputs. We'll do the analog parts in a moment. And then here, we're setting one of the outputs for 50 microseconds. There's a delay there. Going to turn the output on. That's a CPU reset coming out. So that's on, turned on. Then you wait 50 microseconds through this subroutine. And when you come back out, you turn it off. And then I'll turn it back into an input. So that sends a reset pulse to all the registers on the CPU. It's sort of the same as pressing the reset button, but done from this end instead. And here we're setting up the analog inputs. So we got analog input 0 and analog input 6. So we only got 2 of them. One of them for the speed control and one for the keyboard. And we turn analog to digital converter on to read them. Then we got clearing the buffer for the LEDs, because we're going to send the data out and we don't want random numbers in there turning LEDs on at random colours, etc. We want it to be nice and blank. And then here's the 256 bytes of RAM. We want to clear, or 512 bytes of RAM. We clear them, but we only can go around 256 times because we do it in 16-bit processor, so it's 2 bytes at a time. Then clear the page pointers, which would normally be 2 actual hardware registers for the paging. If you was going to do a ROM and a RAM chip, you'd also have to have a 8-bit latch register in there for you to put the page number in for the top addresses on the ROM and RAM chips. So that's what I'm emulating here. So we need to clear those. So the virtual I/O is at this address. So we clear them out. It repeats 5, means do that 6 times to put the 2 zeros in there to clear them all out to make sure that it's 0. So we're always going to start at ROM page 0 and RAM page 0. And this part here is just setting up the timer, and it's going to do, when it counts to 16,000, it's doing 1 clock pulse per instruction. If you're running at 16 MIPS, that would be 1 millisecond. But we're running at 8, so that ends up with 2 milliseconds. So the interrupts every 2 milliseconds. Plus the counter of 10 gives us 20 milliseconds scan rate for the keyboard, etc. And here we have to set up a value in the random number generator to start with, because if it starts at 200, or if it started at 0, we have to go all the way around 255 before it did anything. So we just put a 10 in there, and the first time it runs, it will knock it down to 9. So we know where we're starting from. And then we call the video update routine to clear the screen. And then this bit of code here, this really should have been in the section above. It works here. I've just got a slightly different loop, so it's just ended up here. This is setting up the microcontroller so it can read its own ROM. You've got various pages and things you have to set up, and in the end we end up with W8 holding the address of here where the first byte is for the ROM code. So I'll get back down to that. There we go. And then the next thing it does is it sets the clock speed. You must have a value in the clock speed, otherwise the timers won't time out and you won't actually run the code. You'll stop, or if it is 0 in there, it could take a very long time before it come around and done the first pulse. So preset your variable and just set a speed in there to run to. That will get updated the first time the interrupt sequence runs and reads the clock speed potentiometer. And if we look at the main loop, that will sets the T states and goes round and round and round. So we'll set T state 0 and then call a subroutine called cycle. And then when that returns from there, we do T state 1 and call that subroutine again. And T state 2, call it again, and so forth down to T state 14 and then call subroutine again for the last time. And if the display needs to be updated, it will call the display, and that's another subroutine. We'll go through these subroutines shortly. And once it's done that, it just loops back round to the beginning. And that will be one instruction cycle, so that's one CPU instruction would have been performed there. So if we look over here, we've got, there we go, move T0, which we know will be a 0, into W5. We pass the value in W5, and we call cycle, which is the routine that's going to do all the things that happen in T state 0. Then when we return, we do T1 and then T2 and so forth through. You notice there's no T7 and there's no T13 because nothing actually happens on them, and there's no T15 either. So once we've done all that, we then check the do vid flag. If that is on, it means the video memory has been updated and we need to update the screen. So it calls the video update and that displays the screen. We only do it when it's been updated rather than every cycle, because this takes a bit of time to do and it would slow everything down. So only do it when needed. So now let's have a look at that cycle routine I mentioned. So every T state will come into this. So the first thing it will do is clear the actual T state going out, which is basically means set it to 15. So there's no T state signals going out to the instruction decoder. And it clears the pulse, make sure there's no pulse on. And then it calls delay 1. So there's a subroutine called delay 1, which will either delay for a period of time, which is set by that speed potentiometer, or it will try to read the F1 key on the keyboard, depending whether you set to auto or manual. And when it's done that, it will come back and it will set the first T state, well, the T state that you passed to it in W5. So the first one, you'd put a 0 out, so T0 would come on. It will then call delay 2. The reason there's different delays, here, 1, 2, 3 and 4, is because the delay is the same if it's on auto, but the key you're looking for if you're in manual is different. So here it'd be looking for F2. When it returns from that, it will then turn the pulse on. Then after that, it will call the I/O function. This is where you're emulating the RAM and the ROM and the IOs, etc. So we'll go through that sequence in a little while. And then after it's done that, it will call delay 3, which again waits a period of time, or for function key 3, and then it will clear the pulse after that. Then delay 4, or function key 4, and then it will clear the T state as input it to T15, so all the T states are turned off, and now everything's back to its dormant state, and it will then return back to the previous sequence. So if we look for the code of that, First thing you do is clear the pulse. Quite easy. And the next one is set T15. All the others are off. That one's on. Some of these comments a bit out of date. Isn't? Oh yeah, there it is. It's 15 times 256. So that's quite a big number. So it's 15, but on the top byte of a word going out. Then it calls delay 1, which waits for the timer, or F1. And once it's done that, it comes back and it moves the T number out. So that's the T state comes on. Then calls delay 2 and waits for F2 or the timer again. Then it's set the pulse. Then it's called the I/O. So this is almost one for one what's going on. So here we go for delay or F3. Then we turn the pulse off afterwards. Here we move a 0 out of port B. So what was on port B is now being cleared to 0. And then we turn it back to being an input. If it was an output, it may have been an input, but we don't know. So we say it here because it depends what T state you're actually running through. Then call delay 4 or F4. And after that's done, put 15 out to turn the T state off and then return. Now here we have the delay routine that was mentioned earlier. There's 4 of them, delay 1, 2, 3 and 4. They're all in the same routine. You just drop into the code at different places. So the first thing we do is set which F key we're going to be searching for, even though we may not necessarily do that. And then we check to see what mode we're in. If we're in manual, we come down and look for that function key. And once we get the function key, we then return. If we're in auto, we just wait a period of time, so many milliseconds, depending on what the potentiometer being set to. Basically, it just calls another delay routine, which is in milliseconds. The bigger the value coming in from the potentiometer, the longer the delay and the slower the processor actually runs. The code for that, quite straightforward. Move number 1 into W1, then branch to cycle delay. That is saying we want to look for F1. Do you remember picky key had 1, 2, 3 or 4 in, depending on the F key? Well, that's where we're going to be checking for it. Come down to cycle delay, and the first thing it does is check whether we're in auto or manual. If we're on auto, we just branch down to the auto section, which gets the clock speed value, which we'd put in there in the interrupt routine, and calls a delay, and just waits a while before coming back and returning. If we're not in auto, we're in manual, we drop through to here. The location of the picky keyboard variable in W3, clear W2, get the byte that picky keyboard contains, so that W3 has got the address of it, put that into W2, then we compare W1 with W2. W1 here is where we put the number for whatever key we're looking for. If they're the same, then we branch out here and exit. If they're not the same, it just branches round again. So it's waiting for the correct key to be pressed. We don't need to debounce on this one because we're looking for just one specific key. And if you switch it back to auto, it will automatically jump out to the auto one. So it's easy to switch between the two if you want to. Now you may recall in the earlier sequence we had this I/O subroutine we called once the pulse had been turned on. Now this is where we actually do the emulation of the I/O and memory, etc. So the first thing we do is we wait 1 microsecond. This is to ensure that any pulses or changes between from the T state to pulse or pulse to T state, etc. is at least 1 microsecond long. To be honest, the rest of the code takes a lot longer than that to run, so this isn't really needed. If all the inputs coming in, so we've got the 4 signals coming into the microprocessor from the control bus, which is the data out or write signal, the I/O line, the read, and the memory chip select. If they're all off, then just exit, because this cycle isn't one that needs any sort of emulation like T2 or T3 states where you're just setting up addressing modes, so you don't actually do any reading or writing. Then first of all we check to see if the data out enable is on, so that means we're doing a write, and the I/O is on. That means we're trying to write to I/O. as in setting the page number, for example. So the CPU is sending to I/O. So we go to this routine. If it's not that, if we've got the read and I/O, then we must be reading from the I/O, like say reading the keyboard value. So we've got to do a sequence that takes that I/O value and sends it out to the CPU. Or if the data out enable is on, which is right, and we've got memory chip select on, we must be writing to RAM. So we do the CPU to memory routine. Or if we've got the read on and it's memory chip select, we must be reading ROM or RAM. So we do the memory to CPU subroutine. And then if it's any other combinations, then there's something wrong. So just exit out of it and don't do anything. If we look at the code for that, over here, we've got, there we go, move 1 into W1 and call delay microsecond. So that means wait 1 microsecond. And there's a little sequence for that, which we'll go through right at the end. And then we're going to put a mask on here in W0, and then we're going to read port C, and we're only going to look at the bits that we want here. So we're going to add them together, compare them if they're 0. So if it's 0, that means they're all off. We just exit out, which is the first step here. If they're not, then let's compare it with number 10. Number 10 is the same as having the data output enable on and I/O on. So that means we've got to do a CPU to I/O transfer. So we branch to that routine. And again here, if we've got a 264, means we're doing a read and I/O is on. So do I/O to CPU that time. If there's a 34 coming in, that means the memory chip select and data output enable is on, which means we're doing a write to memory. So it's CPU to memory. And if we've got a 288, it means we're doing a read, CPU read for memory, because we've got memory chip select on and we're doing a read. So do that subroutine. If not, then just branch out saying, just leave because it must be something else and it's wrong. It shouldn't have been called. There's an error somewhere. So that's that sub part of it. Now let's look at these individual little steps here. So the first of those subroutines is CPU to I/O. What we're going to do is we're going to read the address and the data. If it's an invalid address, then we're going to exit because we only emulate 12 bytes of I/O. You could have 256, but I haven't actually emulated that many, so I don't do it. Then I'm going to calculate the virtual address. This is where it's stored in the microcontroller's RAM. And then we're going to put the data there. If you're doing it hardware, you'd actually be writing to a physical 8-bit latch somewhere. So let's save the data and then we'll return. So we look for the code here. So we need to emulate all that. That's done here. So we're on CPU to I/O. First of all, we set port B to all inputs. And then we're going to read it in there into W1. W0 here, we're setting it up as a mask because we'd be wanting to split off the top and bottom bytes. So one's data and one's the address. Here we're going to AND them together and we'll end up with the address in W3, but it'd been a top byte of W3. So we swap them over. So W3 has now got the I/O address in it. And you do the same again, and the W2 has now got the data in it. So we compare the address here with 11, and if it's greater than 11, then the number's too big, so it's an invalid address. We don't emulate above that address. So we'll go to I/O done, as in basically exit out of the I/O and don't do anything. If it is within the range, then we get where the virtual I/O is saved in the RAM, or then in W0. Then we add that to W3, which is our address coming in. So if we wanted to go to, say, I/O port 2, we'd add 2 to that address, and it'd be 2 bytes further up in memory from there, as you remember from where we showed you where the variables were defined at the beginning. And then we take the byte that's in W2, and we just place it in that address, and that's basically take the data from the CPU and pull it into our virtual I/O. So now we're done, and we just exit out. next on the list was I/O to CPU. So we're going to read the address, calculate the virtual address where the data is actually stored, click that data and send it out to the CPU and then exit. So this one's a little bit shorter. So we want I/O to CPU. Again, we set up our mask to cut off our address and data. So here we are setting up a mask for the address, and we move that into the Tris B. So that configures the I/O port. So half of port B is now an input and half of it is output, because we're going to be putting data out onto the data bus. Read what's coming in, so we get the address that we want. And here we go, masking it off to make sure we've got nothing in the top, swapping it around into the bottom byte, so the address is in the bottom byte of W3. We then find where the virtual I/O is, and then we add that to the address we just got to find the actual address in RAM where the data is stored. We then clear W2 to make sure there's nothing in it at all, and then we get the byte that's held at the address in W3, which is the emulated I/O byte, and we put it into W2, and then we can't move this direct, and then move W2 out the port. So we're basically setting the data bus to whatever value was held at this address, which is the virtual I/O. So we leave that output on. Now this is done just as the pulses come on, and we know we can leave the data there, and the data will get strobed in on the next part of the sequence where the pulse goes low. So we leave the data there. So we now branch to I/O done, we're all sorted. And that's the I/O to CPU routine. Quite simple and straightforward. Next we have CPU to memory. So this is writing to RAM basically. So we're going to read the address and we're going to read the data. We're going to see whether it's a ROM address. If it is, then exit, because you can't write to ROM. Then we can see if it's a video address. If so, set the flag to say the video will need to be updated because we're writing to the actual video memory. And we'll calculate the page address for the RAM and put that with the read address coming in, so we know exactly in the actual RAM where to write the data. And then we're going to write it there and then return. We scroll down to CPU to memory. We're setting the mask to FFFF, and so we're setting all the port B to inputs to make sure they are. Then we got set the mask to so we can split off the address and the data. And we read port B in, which has got the address and data in it. May recognise this code from previous. Add them together, swap it over, so we now got the address in W3. We now move 239 into W0, and we're going to compare W3 with that. So this is where you're checking to see whether it's RAM or ROM. If it's greater than 239, then it's RAM, so we go to the RAM routine. If it's less than 239, then it must be ROM. Or 239 or less, it must be ROM. And so in this memory arrangement, we leave at that. If you'd split your memory 50-50, so you've got 128 bytes of ROM and 128 bytes of RAM, that value there would be 127. This is just to make sure you're only trying to write to RAM. So depending on what RAM you got, depends what value you put in there. So if it is RAM, in this instance, our video RAM is on bytes 241, 242 and 243. We'll see this a bit later in the description as to what's going on there. But if it's on any of those 3 bytes, then basically we call this bit down here, which sets this flag on. Bit set, do vid flag on. So the next time the circle comes round, it'll see this flag on and it'll update the screen. If it's not, it just jumps over it because we're talking to a different bit of RAM and there's no need to update the video, it hasn't changed. So here we're going to mask off the address with just FF with just the bottom 4 bits into W3 because it will have other bits for higher up, but we don't want them, we just want like the RAM address. And then we're going to mask off the data coming in and put the data into W2. So that's be the bottom 8 bits of W1, which is the whole port you've read in. So we've got the data in W2. Then we're going to find the RAM address, so in W1, and we're going to add W3 to the RAM address. So this is basically how many bytes offset, but that's just the RAM address. But now we've got to read what page we're on. So find virtual IO, read the second byte of virtual IO, so that's byte 1, which is the RAM page, and we make sure W0's got nothing in it, and then we read the RAM page into W0. We then shift left W0 by 4 bits because we want like a 12-bit address, not a 16-bit address, because we punched all our 16 bytes of RAM all up together so they take up less space. So this is just calculating the address for that. Add W3 to it, which is the offset bit, and then grab that byte. Then we move the byte of data we've got into that address. So we've now written into the RAM. And then we've finished here. Next subroutine is memory to CPU. So basically read what's in the memory, be it RAM or ROM, and send it out to the CPU. So we need to read the address we're being asked for. Is it a ROM address? If so, calculate the ROM address page and send the data, and then exit. If it's not a ROM address, it must be a RAM address, so calculate RAM address and send the data out. We can't use the same calculation on these because this is in 256 byte chunks, this is in 16 byte chunks, so this has to be calculated a bit just like previously. If we get to that bit, the memory to CPU, again reading the addresses, etc. So we've now got doing the same sort of thing. We've got address in W3, checking to see if it's RAM or ROM. If it's RAM, do the RAM sequence. If not, go to the ROM sequence. So we start with the RAM one. Again, just the bottom 4 bits. This is all pretty much the same code as we just looked at, working out the virtual IO address and the offset for it, and then taking the byte that's there and actually putting it out onto the data bus. So we take the RAM value, put it on the data bus for the CPU to read. And then the ROM is a bit easier because working out the address is what is in your page, ROM page, and then just adding the address straight to it. In the RAM here, we had to do this little shuffle over by 4 bits for the RAM page. Here we just add the two together, and that gives us our offset to actually read the ROM. So it's using W8, which we defined right at the beginning. That W8 is never used for anything else. That holds the base address of the ROM at all times. Calculate that and put that out onto the bus. Then the exit IO done. So that's the memory to CPU read. So that's the RAM and ROM emulated now, which is the most important part. And now we need to go through the display routine. First thing we do is disable the interrupts, because sending the information to the serially addressable LEDs is time dependent and we don't want to be interrupted in the pulses because it will corrupt the data. The first thing we do is calculate the data we're going to send for the first LED. And then we're going to do that all the way through for all 9 LEDs. And we'll end up with 27 bytes of data. Then we'll set up a loop that does steps through the 27 bytes. And another loop inside it will send through each bit, because each bit has to be sent out individually. In the previous video I showed the data sheet for this. We'll be sending out 27 bytes of 8 bits. And they'll loop all the way around, pulse out. And when that's finished, we turn the interrupt back on again. So if we look at actual code for that, we've got, here we go, we stop the interrupts, turn the time 1 interrupts off. We then find the beginning of RAM and we add 1 to it because we know the video RAM starts at address 241. The RAM starts at 240, so we know it's just 1 offset from it. We'll then set up a buffer. This is a 27 byte buffer. It's actually defined as 30 bytes, you might recall, but that's where we're going to be starting. So the buffer address is in W3 and where we're reading from is in W0. They're set. We now call a routine called first data point. This converts the very first square on the noughts and crosses into the data that needs to be sent to that LED. and the second data point is the next one across, and the third, that'll be the top right one. We then update the RAM pointer to point to address 242, which is the middle row going horizontally. So we do the first one on the left, then we do the second that's to be the middle square, and then we do the middle right square, and then we move down to the next address, it's 243, and do the bottom left, bottom middle, and bottom right LEDs. So we've called that 9 times, and each call creates 3 bytes of data, so that's our 27 bytes of data we need to send to the LEDs. First thing we do before transmitting is this is the actual output. So that's port C, and DISP is, I believe, on 9, so bit 9 of port C is turned off, and we hold that off for 50 microseconds. So on the data sheet it says you must have at least 50 microseconds before packets of data, otherwise that's how it knows it's the end of the packet. So we're just waiting to make sure everything's cleared down and we're stopped before we send anything else. Where's the buffer for our data we're going to send? We put in W1, and we're going to be doing 27 bytes, and then 7 is W3 because that's going to be our 8 bits. So we're going to test each bit as we go through. So if it's a 1, we're going to send short pulse, which is here, it turns the bit on, and then it's going to turn it off and branch down to the next bit, which loops all the way around. Whereas if we're going to do a 0, we're going to do a shorter pulse and then a bit more of a delay before we turn it off again. So this is your long on, and then loop round gives you the short bit coming back. And on 0, that's your short pulse on, and then a longer bit coming back. We do that for every bit, and then every byte just looping around. And then the last thing we do before returning is we turn the interrupt back on and return, and that's sent out our stream of bits to the LEDs on the display. Now, if we look at the structure of the video RAM, it isn't really video RAM, it's just some of the variables that are used by the noughts and crosses program. It just happens to save in bytes 241, 242 and 243 the information we need. And when we go through the noughts and crosses program, you'll see how this all fits in. There are actually 8 bytes of data that it uses, but we only need the first 3 to see what the grid should be. So here's like the grids. We've got A, B, C, D, all the way to I. That's your 9 squares in your noughts and crosses. So byte 241, bits 0, it's got C in, bit 1, it's got B in, and bit 2, it's got A in. In fact, it's got other bits as well. So this is the player data. So if the player presses the key for this one up here, which is the 1 key, I believe, you'll get a bit set there. If when the CPU is playing, it decides it uses that square, it would put turn that bit on there. So that one and that one will never be on at the same time, but one of them will be on. So if those 3 bits are on, then that's a winning line, and the noughts and crosses program will detect that. But we're just interested in whether these bits are on or off. If that one's on, make that LED red, or if that one's on, make it green. If neither are on, then leave it turned off. And the same for these bytes here. So they actually have these are the values that be in there. When we're running the game, it will actually be looking at these values. Like if it sees a number 7 in here, it knows that the player has won. Or if it's got a number 56 in there, I think that is, yeah, then it knows the computer has won. We'll just be looking at the bits in this bit of code. Now, if we look at the code that generates the information that needs to be sent to the LED, we've got this. So when we call first data point, we come here. First data point, second and third is all in the same routine. They're just different entry points. What we do is we'll set the brightness that we're going to turn the LED on to. And then if bit 5 is set, then we set up that it's going to be green and return. Or if bit 2 is set, then we set it going to be red and return. Or if neither of those are set, we just set it as black and return again. So we're just building the data to be sent out to the LED. So the first thing we do is put a 0 in 4, because that means off. And we put a 64 in 5. This is the brightness. When I first wrote this, I put 255 in there, which means turn the LED full on, and it was way too bright. So I knocked it down to 64. We then clear all the data out of W2, and then we get the data byte we want. So W0, we come into this routine with the address of the video memory in there. To start with, it'll be 240. Next time we call this, it'll be 241, and the one after it'll be 243. We read the byte in, and then we check to see whether bit 5 is on or not. If bit 5 is on, then we set everything to green. We're going to go down to routine for loading green. If bit 2 is on, we'll load red. If neither are on, then we load black. And then second point here, this is the next bit over. So this is bit 4 and bit 1, or bit 3 and bit 0 for the right hand LED. So that would be, start with, that would be square A, square B, square C, and that'd be square D, E, F, G, H, I, each time it's called. The data is just saved in a continuous block of 27 bytes, starting at W3. If we've got a black, we're coming out load black, and W4 has got a 0 in it, so we're going to put a 0, another 0, another 0. So it'll be 3 zeros in the buffer there. And then we're done, so return. When we come back in again, say if it was a red, when we come to red, the first byte will have the brightness value we put in here. So it was a 64. We put a 64 into the next part of the buffer, and a 0 next and 0 next. So we've got red is first, green is second, and blue would be the bottom one. If you wanted blue, you put the value in the third byte. So that's for red. For green, as I say, we put it in the second one there. So we've got 0 of red, 64 of green, and 0 of blue. If you wanted to change the brilliance, so you change the number in W5, you notice the green comes a bit brighter than the red, or you could change the value that gets written on the, instead of putting that value in, you could put an actual number that gets loaded in. And that's how we calculate the LED. So there's the first, second is bit 4 and 1, and the third is bits 3 and 0. There's a few other odds and ends of code in here. There's this delay X, which is you pass a value to it in W0, and it then does a loop inside a loop, and this is calculated to give you 1 millisecond delay when running at 8 MIPS. So let's just say looping around with some knobs in there. And this is the delay for microsecond, where it's just a few knobs in there every turn, because you only need 8 of them for 8 MIPS. You'd need these other ones if you was running at 16 MIPS. This is where I had to patch my CPU. I bought the microcontrollers off eBay, and I thought I damaged a couple of the pins when first soldering it in, and I had to put those little red wire links in and put this patch code in so I could actually run things, because port B and port A had some faults on. And then after I'd blown the motherboard up with the 40 volts I put on it, I had to build a new one. I had exactly the same faults. So I've come to the conclusion I've either got fake chips, or these ones were rejects that somebody's got hold of and sold on. I mean, if I'd known those I/O were dead, I would have built the board slightly differently. So only buy from a reputable dealer. Don't get caught like I did. So that's just some patches that I need on my board, but if you was to build one of these and got a decent chip, you wouldn't need these patches at all. In fact, the code's set up so it doesn't call these at the moment. And then this bit here where it's writing 6 and 7 and reading 6 and 7, this was the bit where I put the wire link across so I could single step the microcontroller with its program up, so that I could test things out, debug things, and still drive data channel 0 and 1 by diverting these other ones to it. So again, you won't need these if you've got your two little jumpers in place. Here we've got the analog read. You just set up the analog digital converter for what channel you want to read. take your sample and then return the value in W0. And the same for channel 6. So one's the keyboard and one's the speed. It just returns a value in W6. Here we've got like the read of analog 6. So this routine actually calls this one down here to get the data. It then does a few compares on it. It's doing the keyboard, so there's a little bit of sort of debouncing done there as well before it returns the actual value in W0 to the main sequence. Don't need that on the speed control because it doesn't bounce around. The actual speed control is biased to one end so that you've got most of the sweep is from going slowly to faster. You can see the LEDs going, but once the LEDs are going too fast for you to see what's going on, there's no point having any speed control there. So this is all biased up one end through the signal that's fed back for the speed control. So it's shifted over and 500 added, etc. So that covers all the bias and glue logic in the microcontroller on the motherboard. So in the next episode, I think I'll go through some of the utilities that has helped to get this far. There's a program for emulating the CPU in BASIC. That saved me a lot of problems. I found quite a few bugs in my instruction decoder with that. And thus, in the end, I was able to build one that works almost perfectly first time. And there's also an assembler for assembling the CPU's machine code and creating the data files that you see here, all these bits here. Instead of hand assembling this, I've got an assembler, and it actually creates a text file like this. I can just cut and paste in to make actually doing the programming of the CPU easy. I'll go through those two in the next episodes, and then we'll get to the actual program for the noughts and crosses to show how that works. So don't forget to like and subscribe, and hopefully I'll see you in the next part.